Hello. We have started our discussion about public key cryptography, where we uh, started about RSA encryption scheme. To create the background for RSA encryption scheme, we have discussed about prime numbers and algorithms for testing for the prime, and also factorization problem, and existing the most efficient algorithm for factorizing. And then we discussed that because factorizing is a hard task, RSA encryption is going to be secure because the base for the RSA encryption scheme is with the hardness of factorization. And that is the information we have discussed so far about this RSA encryption scheme, which is basically coming under the public key encryption or public key cryptography category. And I have skipped many details about the algorithms, how they work, because you can easily go through the slides and understand them. And also the CO 3 to 5 course is to introduce you the basics of cryptography and what are the things we have, and how we can apply them, and what are the purposes, rather than going deep into the building blocks and the mathematical basics of these things. That's why I skipped a lot of details about the proofs and the algorithms. But if you are still interested, you can go through them, and you are free to come and meet me, or you can't come and meet me because of this current situation. But anyway, you can email me and ask for my guidance or anything if you are still interested in cryptography. So cryptography is it is basically coming from mathematics. It's kind of applied mathematics subject field, and which is very much applicable in our information technology, computer science. And computer science is itself kind of more towards mathematics, and as well as computer engineering. So this cryptography is like, it has very big mathematics core, but there are a lot of computer engineering, computer science people who do computer science and then go for cryptography, even without, they are not coming from the mathematics. But there's another branch of people who are doing their basic or the bachelor studies with pure mathematics and then come to cryptography. So what we have to understand is cryptography is very much mathematical, but a lot of applications. So if you have programming skills, how to do program, how to implement, how to deploy the secure systems, and if you have the deep understanding about cryptography, that is really beneficial. There are not a lot of people in the world who can do the both, the programming part and cryptography. Mostly people who are doing programming, they are coming under computer science or computer engineering or IT. And people who are doing cryptography, the theoretical cryptography, algorithm designs, and building the encryption schemes, and the fundamental, the foundations or the protocols for cryptography, they are coming from the discipline of mathematics. So coming to the point that where the both fields are connecting is very important, and like very much demanding thing in the world. So I invite at least one or two people from your batch. If you are really interested in cryptography, try to be a person who is connecting both the fields. programming and cryptography. So it is very demanding thing. Anyway, so we have discussed about finally how this RSA works, and then I skipped the discussion about how to prove the correctness of RSA. So I leave it for you if you are really interested in understanding that thing. And then I think it's better to a little bit of discussion about Chinese remainder theorem and how we can apply that for RSA scheme. So Chinese remainder theorem, I think you have heard that in your basic mathematics courses. So this is the Chinese remainder theorem, and I'm again not going to discuss about the details of Chinese remainder theorem. What I'm going to say is how we can apply that, what is the application of CRT or Chinese remainder theorem in RSA computations. So first let's look at the RSA applications. The RSA operation can be used in a variety of applications. In this lecture we consider only the message encryption as encryption scheme. So we can use RSA as a public encryption scheme. And also RSA is often used to distribute a key for symmetric key encryption. So we kind of discussed that thing on and off when we are talking about RSA. Since RSA is expensive computation, we are not using RSA very much for data encryption or streaming or whatever, for data encryption. It is used to encrypt key materials and distribute key materials between parties. And then that key material will be used to derive a key which can be used for symmetric key encryptions like stream ciphers or block ciphers. So this RSA is used for distribute a key. So one application is for key exchanging, and also we will discuss about RSA as a signature scheme in our next lectures. So RSA can be used for authentication by proving knowledge of the private key corresponding to an authenticated public key. So that means like if I RSA can be used to provide the knowledge of the private key by corresponding to an authenticated public key. So that means since RSA is a public key encryption scheme, somebody can encrypt a value and send to another person, and the other person can only decrypt it if he owns the private key corresponding to that public key. And then if he can decrypt it and show the plain message sent by the sender, the receiver can prove or show that he has the knowledge about the private key corresponding to that public key. So some kind of a proving scheme RSA can be used. So these are the applications of RSA, and you can see that these kind of things can be done because RSA encryption and decryption uses two different keys, but they are related mathematically. And implementation issues of RSA. So we have to optimize in the implementation of RSA for better use, for secure use. So some of the things like the most important issues are key generation, and there the choice of E, the public key, and generating large primes. So they are the things that the engineers or the programmers have to really consider when implementing the RSA. How to choose the E value. So E is the public key, and E should be small enough to do the encryption efficiently. But for the decryption key can be larger. So for the decryption, the purpose is security. Nobody else should be able to get the value of decryption key and decrypt all the messages. So there we can sacrifice the efficiency and give focus more on the security. So that means we can use large D values, or the decryption keys that will give add more cost for the decryption operation, but still if we can maintain the security, that is beneficial. But for the encryption key is public value, everybody knows that. So we have to make that small as possible to make the encryption operation efficient. And generating large prime numbers. How to generate large primes? So numbers are there. What we have to do is we have to choose the numbers randomly. When we choose a number, what we have to do is that prime number should be large enough in a way that we cannot factorize the product of two large primes. And other thing is we have to find out, or we have to have the guarantee that the large number we choose is really a prime number. It should be a prime. So those are the issues coming into the picture when we do the implementation of RSA. We have to have efficient and reliable algorithms for these things. An encryption and decryption operation. So encryption should be fast enough to do the exponentiations efficiently, exponentiation computations. So for that, we can use the CRT, or the Chinese reminder theorem in the decryption operation to make it faster. So I told you that E should be smaller enough to make the encryption operation efficient. Since E is a public value, we know that everybody knows E value. So it is useless to have, it is not very meaningful to have E value larger and larger to make the encryption operation inefficient. So we have to make the encryption operation efficient as possible by choosing the E value small as possible. So we can do the encryption operation efficiently. But when we have the D value, we have to make the D value large as much as possible to make the RSA scheme secure. So that D should be large enough in a way that it is not possible to guess it easily. So when D is going to be large, the exponentiation computation we use for the decryption operation is going to be inefficient, or we can say it is expensive. We have to do, since D is a large value, we are computing the exponentiation operation for a large number, large power. So we have to make it efficient. To make it efficient, we use Chinese remainder theorem. Using Chinese remainder theorem, we do the computation efficiently and make that decryption operation more efficient than the normal RSA decryption operation. And also, we have to consider about formatting data. How to format data. That means how to add some padded values to make this more secure. We'll discuss about that in our coming slides. Okay, so now you will see the application of this Chinese remainder theorem in the context of RSA decryption. Okay, so these are the information about the things we discussed. So generating P and Q, the large prime numbers, the primes P and Q should be random of a chosen length. This length should be at least 512 bits. So P is a 512 bit number, Q is a 512 bit number. That means large primes. A simple method of selecting a random prime is given by the following algorithm. There is an algorithm we presented here, and then once the algorithm is used to choose a prime number, we require at the point 4, it is said that we require a fast way to check for primality, such as Miller-Rubin test. So that testing for primality should be reliable enough and efficient enough. So we have to consider those things when we implement RSA scheme. And are there enough prime numbers? So this information is a little bit more theoretical, but it is said that the prime numbers we have in the pool, or the in real numbers, that is enough to make a lot of random prime choices for the RSA users. So 1, 2, 3, at the point 4, it is said that according to the prime number theorem, there are a lot of prime numbers we can find. Like, there are a lot of large prime numbers we can find. So we can estimate that 1 in every 355 numbers of size 512 bits is a prime number. Therefore, there are well over 2 to the power 500 512 bit prime numbers. So that is more than enough to use RSA, like give random choices for prime numbers for RSA usage. Thus, the last point said, thus brute force searching for randomly chosen prime is impossible. So there are 2 to the power 500 choices of prime numbers for the pool of 512-bit large numbers. There are a lot of prime numbers. We have enough prime numbers to be used in RSA. And this information is about some practical problems with RSA key generation. So one thing is, in 2008, it was discovered that the implementation of OpenSSL used in Debian Linux systems used massively reduced randomness for RSA key generation. So one important thing in this key generation is the randomness. It should be completely random, like random as possible, as much as possible. So if that randomness is not there, if it is like very deterministic, closer to deterministic, or the like choosing the P and Q, it is said that we have to choose P and Q random. But if that choice is not that random and predictable, the security of the RSA encryption scheme is reduced. So this one problem is there, mentioned in the first point. And in 2012, a group of researchers led by Lenstra is a mathematician, published a study of over 6 million RSA keys deployed on the internet may have expired. So that is like expired keys are there in internet. So that is also a practical problem. Okay, so I have discussed in few slides ago the key generation. The choice of E is important. So selecting E, the public exponent E should be chosen at random for best security. A small value of E is often used in practice since it can have a large effect on efficiency. We know that. E equals 3 is the smallest possible value and is sometimes used. However, there are possibly security problems. So therefore, the popular choice is E equals 2 to the power 16 plus 1. That is the possible choice. So E is randomly chosen value. P and Q are chosen independently, and N is generated as a product of P and Q, which are two prime numbers, two random prime numbers. And then we choose E value. So E can be anything independent from P and Q. So here it is said that selecting 3 as E value may be too small and give some security problems. So E has to be large enough but not very large to make it efficient. A smaller than average D value is also possible. However, to avoid non-attacks, D should be at least square root of n. So these are the things understood by practically using the RSA scheme, and then only people could understand possible ways of attacking the system. So once we consider these kind of scenarios, it is possible to implement an RSA scheme by choosing the relevant parameters in a way that it is not possible to break easily. So that preserves the hardness problem, the assumption of that hardness problem. That means once the hardness of factorizing is really hard, then RSA is going to be secure. Given that we choose the parameters carefully, not by not allowing the attacker to find loopholes in breaking the things. So smaller than D, average D value is also possible, but however, to avoid non-attacks, D should be at least square root of n. N is the product of P and Q. And this slide says how to do the fast decryption using Chinese remainder theorem. I'm not going to discuss that, but keep in mind Chinese remainder theorem, that concept is used to make the decryption operation faster in RSA scheme. So there, in previously we, like in normal RSA, we use C to the power D mod n, but here we are not using n as it is. We have to use P and Q separately for this decryption operation. Okay, and this is information about why that Chinese remainder theorem works for make the decryption more efficient, and how much faster is decryption with CRT. So it is said that overall there is about 4 times less computation when CRT is used instead of that normal RSA decryption. So that means if MP and MQ, that means this MP equals CD mod that thing, and MQ is this other thing shown in this equation. So if those two things are computed parallelly, the time can be up to 8 times faster than using the normal RSA decryption. So using Chinese remainder theorem concept to decrypt RSA values can make it up to 8 times faster. That is significant improvement. And also we have to discuss about the importance of RSA padding. So using the RSA encryption function directly on messages encoded as numbers is a weak crypto system. It is vulnerable to attacks such as building up a dictionary of non-plain text. We know that without padding, without adding some randomness to the message, this is going to be like very deterministic. That means if we have a plain text and for a given key, it will always give a particular ciphertext. So then the attacker can collect the values for ciphertext and corresponding plain text and create a dictionary. So using that dictionary, once he sees a ciphertext, he can think, okay, according to the dictionary, this ciphertext matches with this plain text given that key is this. So it is possible. So building up a dictionary of non-plain text and guessing the plain text and checking to see if it encrypts to the ciphertext, and Hȧstad attack. Hȧstad attack we discuss in the next slide. So therefore, padding mechanism must be used to prepare messages for encryption. So before encrypting a message, we have to do some kind of a padding. That's kind of like we are packing a thing before the delivery to this encryption algorithm. So these mechanisms must include redundancy and randomness. So padding is basically to give some randomness to the message, plain message. So because of that randomness, RSA encryption is shifting towards what we call like not non-deterministic, not deterministic. It is going to be randomized encryption. Okay, so now let's look at Hastad's attack. Hastad is a cryptographer, I think, from Sweden. So suppose that the same message is encrypted without padding to 3 different recipients. So suppose that public exponent E is used by all recipients, and then the cryptanalyst has 3 ciphertexts like this. So C1 is the ciphertext, the message is the same message, we don't know that. That means m to the power 3 mod n1. N1 is according to the choice of P and Q of that particular recipient. And the next recipient, ciphertext is C2, m to the power 3, because public exponent is 3 in that recipient as well, and mod n2. N2 is the according to the choice of P and Q of that recipient, and similarly to the third recipient, like this. And if you have these 3 equations, let's say we have 3 recipients, they all are using public exponent E equals some value, the same value, and for the same message they will get 3 ciphertexts, but we know that message is the same, E is the same, and what we don't know is n1. We know that n1, n2 and n3, but what we don't know is factorizing of this n1, n2 and n3. So even though we don't know that, without doing the factorizing, we can choose these 3 equations using the Chinese remainder theorem, and we can obtain the value for m3. So then n can be found taking the cube root of that value. So this will happen if we don't use a padding scheme before this encryption. So if we use a padding scheme, that means we are not doing the encryption directly to the message M. So M will be padded and some kind of a random thing is generated there. Then this Hȧstad attack is not possible. So there are three types of padding. So one thing is PKCS number one, that is very simple and ad hoc design for encryption signatures. But in 1997, I think there was an attack proposed against this PKCS 1 padding scheme. As far as I can remember, that is because I don't know, I can't remember now, but maybe you can read about this PKCS 1 scheme and attack on that. Attack is there. So because of that, RSA OAEP, the optimal asymmetric encryption padding, is proposed. So this is actually designed in 1994, and this came into the usage rather than PKCS 1 padding. So this is designed by famous cryptographers Mihir Bellare and Philip Rogave. Both are American cryptographers. Bellare is in University of California, somewhere, and Rogave is another famous cryptographer. So they also worked for Microsoft and several other places during their sabbatical leaves. So actually the Bellare contributed very hugely for the recent developments of cryptography and information security. So this RSA, the OAEP padding scheme has a security proof in a suitable security model. Because of that, it is guaranteed. But PKCS1 is just ad hoc design, not with a security proof. So this OAEP standardized in IEEE standard specifications for public key cryptography. So this is standardized after this PKCS1 is vulnerable to an attack. So this is how PKCS1 works. What it does is first add 00 bytes, and the second place 02 bytes, and PS is the pseudo random string, and then 00 bytes again, and then D is the data to be encrypted. So this is the padding scheme. So this first 00, 02 are fixed, and then we have a pseudo random string, and then we have 00. Once we have this, anybody who knows the this structure can identify this portion is the message and these are the padding scheme. So this is pseudo random thing. Because of that pseudo random thing, what the message is, the M value is going to be randomized, and we can avoid the Hȧstad attack. So length of the block is the same length of the modulus, and PS is a minimum 8 bytes, and byte 02 and padding ensure that even short messages result in a large integer value for encryption. So this is to make that the message is larger enough, even though the data to be encrypted is a very small value. And then OAEP scheme is it is not simple like this. It has some kind of the message and some values, some 30 values are there, and then do XOR operation, and some randomness is there, and there's a function, and that's kind of a complex thing. So first concatenate this M and 3 zeros, and then there's some randomness value, and send it to the function G, and output of that function, and this concatenated value will be XORed and send that value to another function, and that value will be again XORed with the randomness R and get a value, and another X value is coming from coming as this concatenation, and then this X and Y will be sent as a message to be encrypted. So it is kind of a complex but reversible operation. So the idea you have to understand is the padding scheme is used to introduce some randomness for the messages, prepare the message in a way that it looks random, and it should be a way that once it is decrypted, the party who decrypts can reverse it because they know the padding scheme. And also potential attacks on RSA. There have been many attacks proposed on RSA. Most of these are avoided by using standardized padding mechanisms. And because of that, we have only two ways of trying to attack RSA, which is well padded and well organized. So that means we have to attack through the basic building principle of RSA. That means either to factorize n or finding the private key from the public key. So we already saw that, at least we saw in the last lecture, that factorizing is believed to be a hard problem. So we assume that it can be prevented by choosing n value large enough. That means P and Q large enough in a way that it produces larger n. So once the RSA scheme is well padded and n value is n and d values are chosen according to this guideline, only way to attack the RSA scheme is trying on factorizing the n, which is going to be difficult given that factorizing is a hard problem to the available computation power in the world at the moment. But one other thing is, this factorizing can be efficiently done using quantum computers. So there are so many researches going on quantum computers. So they have actually created some quantum computers which can factorize smaller numbers, but once they are developed in next 1-2 decades, RSA will be gone. Security of RSA will be gone because factorizing is no longer a hard problem when the quantum computers are available in the world. So in cryptography, there is another branch which is called post-quantum cryptography, to design cryptographic algorithms, encryption schemes, protocols in a way that they are secure against quantum computers. So one that kind of branch is lattice-based cryptography. So most of the cryptographic algorithms designed using the lattice principles. Lattice is a mathematical structure. Lattice structures, that basics cannot be easily solved using quantum computers, even using quantum computers. So that is kind of a branch that will have a demand in future. So if you are interested in cryptography, first learn these kind of basics and then try to switch for quantum safe cryptography in your higher studies, and that is a real good thing. So how secure RSA is? If an adversary can factorize the modulus n into its prime factors, then the adversary means the attacker, the algorithm that is used to attack, can easily recover the private key D and reveal all messages. Thus breaking RSA is not harder than factorization problem. So this is very cryptographic way of writing statements about security statements. Breaking RSA is not harder than factorizing the RSA problem. So we are trying to, uh, uh, when we consider the security of some cryptographic scheme, we try to reduce its the hardness of breaking that to a hardness of solving a non-mathematical problem. So the non-mathematical problem here is factorization problem, and we know that there is no known algorithm to do that thing efficiently. There is no known algorithm which can uh, solve the factorizing problem in polynomial time. Because of that, we can see that security of RSA is reduced at least to the level of hardness assumption of factorization. So we depend on that RSA is at least harder than this. RSA is like not harder than this, not harder than, but there is a there's upper limit of RSA's hardness. So using a formal definition of encryption security, it can be shown that breaking RSA is as hard as the so-called RSA problem. So I'm not going to discuss about RSA problem. RSA problem is how to do the, given that the RSA algorithm and E value and D value, using E and how to find out D. That's the RSA problem. There are many cryptographic terminologies here. I'm not going to give very much detailed discussion about those things. Instead, I'm trying to give some kind of a basic flavor about the subject. So it is unknown whether the RSA problem is as hard as the factorization problem, but remember that it is also unknown whether factorization is really computationally hard. So these kind of statements may confuse you, but the idea is here, for the factorization problem, we don't know whether there is another algorithm that can solve or do the factorization efficiently. We don't know that. And for the RSA problem also, we don't know whether there is another way of solving the RSA problem. That means given N and E, finding D. We don't know. But only thing we know is just RSA is based on factorization, and only way we know that if we break the if we can break the if we can solve that factorization problem, we can break RSA. That's the only thing we know. Then we try to like at least reduce the security of RSA scheme to the level of factorization problem. So since there is no algorithm to do the factorization efficiently, we say there is no algorithm we know to break the RSA scheme. There is no known algorithm. So that is what we believe at the moment. Perhaps somebody can find out another algorithm which can solve the RSA problem without doing factorization. We never know, but for the time being we don't know. So one positive security result shows that finding a private key is hard for the adversary as factorizing the modulus of n. Okay, so these are some theoretical stuff. I'm not going to give you detailed discussion about these things because this course is not for cryptography. This is for computer security. Generally, we have to identify what are the cryptographic algorithms and schemes we can use for our security purposes. If you are interested, you can really find out this information, and if you have any questions, let's discuss separately than from this course. And these are the other attacks on RSA, the quantum computers I told you. And the other thing is timing analysis. So this is coming under the category of side channel attacks. I think I have discussed a little bit about side channel attacks in a previous lecture. So what it does is, for the decryption operation, if the attacker can measure the timing for different decryption operations, attacker can have some idea about size of the, not the size, let's say, like how the bits are changing in that D value. So first, attacker can measure that for some known D values, and then having that timing information for unknown value, attacker can get some prediction about how the zeros and ones are going to be changed, how many changes are there. So based on that, attacker can reduce the brute force, the pool to do the brute force search and find out the D value easily. So this is coming under the category of side channel attack. So the timing attack is a side channel attack itself, and these kind of attacks are done on the not on the theoretical design, but once the thing is implemented in a system, these kind of attacks are possible because information are leaking because of the implementation restrictions. As a precaution for that, there is another branch in cryptography which is called leakage resilient cryptography. So that means into the design we introduce some kind of randomness operations, randomness things to make the computation do some random stuff. So that way, this leakage information is not really helpful for the attacker to find out the useful information, because there are a lot of randomized operations are coming. So at least we are trying to, like, for every D value we try to kind of give same time for the operation, that sort of thing. So there are in leakage resilient cryptography is the doing the precaution for this kind of leakage attacks in the theoretical way, but there are another mitigation techniques which is used at the engineering level or the implementation level. There are some kind of like injecting some loops and things and make this timing attack not possible by giving at least, like, making it a fixed time frame thing. But they are not very that kind of engineering solutions are not very helpful, because there is no theoretic, no proof or guarantee about that. There are another ways to filter out that sort of precautions and collect the useful information. So therefore, the more focus is the leakage resilient cryptography, which is coming with proper security proof for the new design, which is leakage resilient. Okay, these kind of information are very much out of syllabus, I would say. I just discussed those things. If you are really interested, you can just chase after these terminologies and find out topics for your future studies or final year research. Okay. Uh, so basically, what you have to learn is RSA is a public key encryption scheme. It is based on factorization problem, and for the factorization, we have discussed about prime numbers and importance of prime numbers and how to find prime numbers, that sort of things, and how the RSA encryption and decryption happens, and what are the practical issues and how to choose the parameters that is important as engineers, and then how to like is there a way to make that RSA decryption efficient. We use Chinese reminder theorem. You have to know that sort of information about this topic. Okay, so I'm finishing off this RSA topic, and as a next lecture we'll discuss about another kind of public key concept, which is called discrete logarithm based ciphers, DL ciphers, that is used for again public key encryption schemes, signature schemes, and key exchange protocols as well. Discrete logarithm things. Okay, have a good day.